By me, section for the watch. So the purpose of this lab is to measure the magnetic field of a bar magnet using on-axis and off-axis magnetic field. And then we're comparing observed and predicted values, where the observed values are from the experiment and the predicted are, of course, from our lovely friend GlowScript. Some general principles is the Biot-Savart law, the magnetic dipole, and the distance dependence. Middle formula is the magnetic dipole, and the B is the magnetic field. And one key thing to know is mu, where mu is the magnetic moment of the dipole. On the bottom right, we have this formula for the magnitude of the bar, and we can calculate by taking the natural log of the magnitude of the bar. We can end up with an equation where we have ln k plus n times ln r, and from there it becomes very easy to solve for, by creating a linear equation, it becomes very easy to solve for ln k and n, and then from there later on to solve for the magnetic moment. So the procedure is, I have this diagram right here, it's the one on the bottom left. Essentially you line up the magnetometer in the smartphone magnetometer, east-west, you can't zero out the X component of Earth's magnetic field. You find the magnetometer sensor in the phone, you measure the magnetic field at various distances along the magnet's axis, and then you plot the results to find N and dipole moment, which I've talked about in the previous slide. And later on you do the off-axis magnetic field measurement. The system is this magnetometer, surroundings is the external magnetic field, and the rest of the Earth, including magnetic north. So here's the procedure. And next up, we record the data. So as you can see on the left, we recorded for different distances. We record the average distance in meters from the phone to the magnetometer, and the average X component of the magnetic field, and we plot this out. From here, we get this neat linear equation where we get ln k, or the y-intercept, is negative 13.754, and then you get the value n, which is the slope, negative 2.7487. So here we get this, and we can calculate mu pretty easily by doing the procedure out that I previously talked about. We end up with mu equals 5.295 times meter squared. Here's the off-axis data. This is very similar procedure, except you calculate the data, you set the d perpendicular constant, and then you displace the phone in the y direction by d perp, and then you get a new value of d. And then from there you can measure the x, y, and z components of the magnetometer in the off-axis direction. And you end up with a b net of about 0.000249962. So here's the code review. So this is the predicted model that I talked about with GlowScript. We input our values for mu magnetic moment, mu mag, and d perp, and average d perp. And as you can see right here by the visualization, the magnet is right here in the middle, and the on-axis is in the direction this way, and the off-axis, which is not parallel to the magnet, goes in the opposite direction, as it's represented by the blue arrows as opposed to the orange arrows. Now, there's lots of error that can go on in this project. The non-exact magnetometer locations, because we kind of eyeballed it, right? It wasn't perfect. Other magnetic interference from, let's say, the floor, or maybe we didn't perfectly align the magnetometer east-west, which created some interference. Additionally, our magnet was very functional, but it had a couple pieces falling off. I don't know how that affects it. I imagine it shouldn't affect it too much, but there could be an issue about that. And then additionally, inexact measurements, because like we said, the magnetometer location was inexact, so we didn't get the exact distance that was required. Now, some observations. So when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. This makes sense because the magnetic field strength decreases with distance, eventually pushing zero far from the magnet. Next observation is as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And that makes sense because the closer you get to the magnet, the stronger the measured magnetic field, especially on the axis of the magnet where the field is strongest. This was seen in the first equations I showed you. Now some discussion. What if we had a compensator for magnetic north and hadn't oriented the experiment? Well, there would have been some interference from magnetic north. You wouldn't have canceled out the magnetic north effects, and you would have had some inaccurate measurements, especially with regards to isolating Bx, the x component. So everything would have been wrong. The k value would have been off, the n value, the mu value, everything would have been slightly off. And then if we were to stick two identical magnets together end to end, you're effectively doubling the magnetic dipole moment, mu. And this would make everything else different, but the direction would be the exact same. So it actually just scaled the experiment by a factor of 2. And thank you for watching. That is the end. Please be under 5.5 minutes.